this AV will impose a twisted gauge transformation on the lattices, on this lattice. AV acts. Oh. This AV certainly is a composite operator. AVG. So it's the AVG that really acts on the triangles. Oh, sorry, the vertices. So let's consider AV an example. In this example, the vertex will be vertex 2, let's say, on such a 3 complex. So vertex first, vertex 1, 3, suppose 4, 5. Suppose this is vertex 2. Let's throw vertex 2 here. Okay, vertex 2. So it'll actually introduce a gauge transformation, but the gauge transformation will be twisted by a phase factor. This phase factor is a I hope I got this right. Maybe this part I need a little reference. There's no way to remember the orientation. I'll explain to you how you get these factors in shortly. And let's remove VP. So VP are just down. Okay. So what this guy does is it changes the original vertex 2 to some new vertex 2 prime. And because the graph is oriented, we got to have some convention of the change. So we always take that the convention that the new vertex is smaller than the old vertex. And now you can see that because this is an operator in the Hamiltonian, you can view this process as a Hamiltonian evolution in certain time dimension, along certain time dimension. And this way, it'll create some new space-time complexes. And there will be exactly 4 3 complexes that are created during this procedure. And these 3 new new complexes will give rise to these 4 factors as the 4 cocycles. Let me show you the picture. This is a must because otherwise you won't have any sense of what's going on here. So I cannot save this time. Let's draw a large graph here. This is original vertex 2. Okay, this is the original 3 complex. And keep in mind that each 3 complex here consists of 5 tetrahedra. So this is 1, 3, 4, 5. Okay, you can count. There are 5 tetrahedra here. And now you add a new vertex here, 2 prime. And then you connect the 2 prime to 2, of course, directly. Okay. this is like along the time dimension, right? You're moving the original three-dimensional slice of space to a new slice of space. So, but this red line is along time dimension. And then maybe use blue color to connect two to all the other original vertices. Now if you count the three complexes that has 2'2 as its edge, there will be just 4 of them. And the 4 of them are precisely these 4. 1, 2 prime, 2, 3, 5, and 2 prime, 2, 3, 4, 5, etc., etc. Okay. And then you know the rule how to assign the orientation to the 3 complexes. Then you can do the trick, and then you will obtain these 4 factors here as the 4 cocycles. And the rest of this part will be just the usual gauge transformation of the gauge group, the group elements along the edges. And I'm sorry I forgot the delta function here. This delta function imposes 2'2 G. So which means this temporal edge should have the group should be labeled by group element G, which is the superscript of the operator here. So this is how you construct the amplitude of the vertex operator. And interestingly, it's not hard to show that these vertex operators, they commute with each other. If V and V prime are different, this V prime. And all the vertex operators, they commute with the phase operators, and it doesn't matter where V is located. So this is 0. And any 2 phase operators also commute. And most importantly, this AV and BF, they are projectors. Okay, they're projectors. So you can see that because of these combination relations, this model turns out to be exactly solvable, because you can just find the common eigenstates of these operators, right? And that solves the model exactly. And it turns out that from this you can see that the ground states of this model will be the common +1 eigenstates of these projectors, AVs and PPs. And those are the ground states. Yeah. I can't hear you.
I mean, your model is very different to the model proposed by
Oh yeah. We are basically working on the same model, but there is a great reduction in their model. They considered only a billion gauge groups. In that case, the mathematical structure is largely reduced, and lots of complexity is also removed. And here, the gauge group G is generic. It can be any group, and we just don't assume that it's a billion. And then derive the ground states spectrum and the modular S and T matrices. So,
can you explain the meaning of the
first equation? Why is there a delta V?
oh, when V and V prime they are the same vertex,
Yeah.
then there will be product rule AVG, AVH. Okay. This guy is actually AVGH. So there's a product rule here. So maybe I should add it here. So it's not so rigorously correct in this equation, but this is what I actually mean.
You mean A squared equal 1? Because that is the relation. A squared equal 1.
The computation doesn't make sense.
Yeah, I think it's complex.
Oh yeah. So maybe I shouldn't write it this way. Maybe just write it 0, and V not V prime. That's more satisfactory. I just want to save a little notion, but turns out to be more complicated. Yeah. Okay. So, having exposed to these, as I just explained about what the ground states should be look like according to these commutative projectors. So we can construct the so-called ground state projector. Let's call this lattice gamma. So this guy will be just the product of all the BFs and all the AVs. And this guy, if the ground states Hilbert space H naught will be simply the states psi that satisfies the relation equals psi. Okay, these will be the ground states. But how can we really find out how to represent these ground states would be the next next thing I'm going to talk about. And why? And we know that there is a subscript gamma that labels that denotes the lattice here. Now to show that this really defines the ground state projector, we would have to show that this guy commutes with some moves that can alter the graph. And indeed, these B gamma 0, they commute with the so-called Hackner moves. If you know about the triangulations of space, you can of manifolds, you might have known that the Hackner moves are those moves on the triangulations that can relate to different triangulations of the same manifold. So if some operator commutes with the Hackner moves, it means that this guy is a topological invariant. This operator is topological invariant. And it turns out that they are indeed topological invariant in three-dimensional space. And then we can define the ground state degeneracy. Ground state degeneracy would be just a naive trace of the ground state projector. Take the trace. And it doesn't matter which graph, which lattice you are on which you are taking the trace, because it's invariant under changing the graph. So you can, for any particular construction, you can actually look for the simplest graph possible. To do this computation, and this is what I'm going to show to you next. So just take the trace, you get ground state degeneracy, and the ground state degeneracy of topological phases are better defined on closed surfaces, or closed manifolds. Now, because now we are in three-dimensional space. So let's consider 3 torus as an extension of 2 torus. And then we can consider a triangulation of a 3 torus. As set, because of this topological invariance, you can consider the simplest possible triangulation of a 3 torus. Triangulate it. Then it's supposed to be like here, here, here. These two guys. 1, 2, 3, 4, 5, 6, 7, 8. Okay. If you identify the opposite pairs of planes, you get a 3 torus. And you can easily tell, as an exercise if you like, how many vertices are there and number of edges and number of face triangles are there in this triangulation of a 3 torus. So there will be just a single vertex, because after the identification, all the vertices are identified. So there is a single vertex. And then there will be just 3 edges. So the number of edges is 3. And the number of faces is this 3. Yes. Number of faces would be, there's a shortage in my brain. Okay, let's forget about it. Worry about later. Okay, but the most important thing is that there will be 3 edges and 1 vertex. Okay. So, and we can label these 3. There are only 3 independent group variables here in this picture. So let's label this K and label this G probably, and another one H prime. The reason why I label H prime has a story, but it doesn't really matter so much. And I still stick to H prime here for your convenience to read my paper. I can change it to something else, but it's better to keep it H prime. Now, a generic state in this Hilbert space, or defined on this triangulation of 3 torus, will be labeled by only 3 group elements, okay, K, G, H prime, because there are only 3 independent group variables. Now, our task is to find out the ground state degeneracy on such a 3 torus, and I would, of course, not show to you the details, but present to you the results, because I don't have time. Okay. So it's better to write down the Hilbert space first. The Hilbert space, the ground state Hilbert space will be a span of such thing, sum over x g. Okay, so such that a state like this would be a ground state. The KH prime will have to commute. Okay, but the original group will be anything, and the ground state Hilbert space will be a span of basis vectors like this. So each of the summation, this average, is a basis vector, okay? Not the thing here, and this may lead you to a faulty statement. Faulty conclusion about the ground state degeneracy, because now you see the original group elements actually don't really matter. What matters are the conjugate classes of these group elements that label the original Hilbert space. Right? So you may, and now you assign the group elements to each of the 3 non-trivial cycles of the 3 torus. So you might want to conclude that the GSD equals the size of the homomorphism space between the fundamental group of 3 torus and the group quotient, some conjugacy relation. And is this correct? And certainly this is not correct, because there's overcounting because of this prefactor here. This prefactor may vanish for certain choices. So there are actually fewer ground states than this possible answer. So this is wrong. But in certain cases, it can go back to this. Okay, now what's the correct answer? To understand the correct answer, we need to introduce a little bit more math here. So this is a, remind you, this is a doubly twisted 2-cocycle derived from the original 4-cocycle omega. So this guy, this beta actually defines a so-called representation, projective representation. So this beta defines a representation on the centralizer of the group elements K and G. So this is a representation of this guy. So this beta, this double electricity two-core cycle, turns out to be a Schur multiplier that defines projective representation. And there is another concept called the beta regularity. So if a rho is beta kg regular, it means that the beta kg h prime x equals kg x h prime for all x that commute with kg and h prime. So this is the beta regularity of the representation, the projective representations of the centralizer of K and G. You know the centralizer group, right? So this basically means all the group elements in the original group G that commute with these two guys, K and G. Now we are ready to present you the correct answer of the ground state degeneracy of this model on 3 torus. T3 equals sum over A equals 1 to sum over B equals 1 or C A. And then the number So this is the correct answer of the ground state degeneracy of this model on a 3 torus. It basically sums over all the beta KAGB regular irreducible representations of the centralizer subgroup of the conjugacy classes A and B. A is a conjugate class in the group G, but B is a conjugate class of the centralizer subgroup of the conjugate class A. The reason why we can label the conjugate classes by, the centralizer subgroups by this class labels is because any two elements in the same conjugate class, their centralizer subgroups are isomorphic to each other. Okay. So this is a correct answer of this model on 3 torus. And now you can see that the GSD completely just depends on beta. Right? It doesn't really directly depend on the original focal cycle that you input into the definition of the model of this topological phases. So when two focal cycles, alpha and alpha prime, which are inequivalent, if they give rise to the same beta, they would just define the same model in the same topological phases. Same topological phase. So having seen the ground state degeneracy, the next step to explore more into the ground state space by checking the modular S and T matrices. So modular S and T matrices. So we know that these modular and T matrices, they actually specify the properties of the anions in 2-dimensional topological phases. For example, this T matrix, it specifies the topological spins of the anions, and the S matrix tells you the braiding statistics between two different anions. And shall we possibly have the same mathematical objects that characterize the 3-dimensional ground states and excitations? So then we got to find out what are the S and T matrices in the 3-dimensional in this three-dimensional model. And these S and T, they will be elements because now we are in 3 dimensions, 3Z, instead of SL2Z. Okay. And this S will be this, and the T would be this. You can choose different generators of the SL3Z group. And this choice is good for future application to dimensional reduce the model to two dimensions along compactifying the Z directions. This is why we left the Z dimension out. And then you can actually also use these 3-dimensional modular S and T matrices to generate pure 2-dimensional S matrix. And I won't do it here. And I can tell you the results.
Maybe you could continue on the way. 5 minutes?
5 minutes enough. 5 minutes enough. So to do this, we need a better representation of the ground state space. So the ground state basis actually can be Fourier transformed because of the representations we just defined into such a form which has 3 labels. Note that originally we have KG H prime here, right? But now we have 3 different labels here. And these A and B will be so-called flux labels, and the mu will be charge labels. And now you can see that in 3 dimensions, you would have some new topological excitations, because there will be an excitation that carries 2 flux labels. And this guys will be a loop-like. So it gives you loop-like excitation. And you still keep the ordinary or like charge excitations. And then there will be also combined flux charge excitations, styons. But these styons, they are loop-like. They're not point-like anymore. So on this basis, this T this T, as usual, still gives rise to a phase factor acting on this ground state basis, which means that this basis is in fact a eigenbasis of the T matrix, modular T matrix. Okay. So this guy may still acquire the meaning of a topological spin for the 3-dimensional ground states. And the S is more complicated, but it's just a combination of the projective characters. So I won't write them down. Okay. So the moral of the story is that these modular S and T matrices, they will also depend on the 2 cocycles rather than the original input 4 cocycles. Yeah. So this explains the redundancy of the group cohomology classification